So now we're moving on towards the Gibbs equations or the property relationships, and this would help us determine the entropy changes for compressible substances and the uh, ideal gases. We have already looked into pure substances. For pure substances, you have to use the property tables to find out the entropy changes. But for compressible substances and for ideal gases, how would you find out the entropy changes? This portion basically deals with that portion of the topic. So Gibbs equation or the TDS relationships, temperature change and entropy relationships, these are the relationships that we'll first derive. For the first law of thermodynamics, for a closed system, a system that is receiving heat and producing work. Now remember, generally the work associated with a closed system is essentially boundary work. So for the first law for a closed system, you know that Q minus W equals to delta U. Heat minus WQ net in minus work net out equals to delta U. Or you could express the uh, uh, just a minute, the sorry, all right, sorry. So the this equation, if you want to express in differential form, we will have this expression in this form. The differential form of an internally reversible process for closed system is del Q internally reversible minus del W internally reversible equals to du. Del Q internally reversible, you know the relationship is del Q internally reversible is TDS, and work internally reversible boundary work, if you remember, is defined as PDV. The boundary work is being defined by PDV. If we incorporate this expression over here and the TDS expression over here, we have essentially an expression which says TDS is equal to change in internal energy plus PDV. This is the first relationship in terms of kilojoules. If you have to express this expression in terms of per unit mass, all the three properties, entropy, internal energy, and specific volume, they would be in specific terms. So you have this as your first TDS relationship. Temperature multiplied by specific change in entropy is equal to specific change in internal energy plus pressure multiplied by specific change in volume. This is the first TDS or Gibbs relationship. The second relationship that we have is based on the first relationship. You know that enthalpy is a combination property of internal energy and flow work, which is PV. And if you want to express this in the differential form, you can say that dH, differential of enthalpy, is equal to differential of internal energy. Plus, if you want to write this expression in differential form, you can have pressure first as the constant and differential of specific volume PDV, and volume constant multiplied by the pressure VDP. Now, if we try to compare this expression with this expression, you know du plus pdv. Du plus pdv is essentially dh minus vdp is essentially equal to, or du plus pdv is essentially equal to dh minus vdp. So we can replace this whole form with dH minus VDP. dH minus VDP, this is the second TDS relationship. Is it clear? Is this clear to you? Are the
Yes, sir.
relationships clear to you? All right. So we have these two uh, Gibbs equations, TDS equations, du plus PdV and dH minus VDP. Now, since these equation contains only the properties, temperature, entropy, internal energy, pressure, specific volume, enthalpy, they are all properties, so they are both applicable to reversible and irreversible processes. And since equation contains only specific properties, that is per unit mass properties, therefore they are valid for both open and closed systems. And if I want to find out the change in differential change in entropy, we can find it out by making ds as the subject of the formula, divide both the terms by t. So first expression is where you have change in entropy is equal to du over t plus pdv over t, and the second expression is where you have change in entropy equals to dh over t minus vdp over t. These are the two expressions that we'll use for both compressible substances, which are solids and liquids, where specific volume doesn't change with the pressure, and you will apply the same for ideal gas. These two fluids, you'll apply these two equations. So how would you apply these equations? Let us first look at the compressible substances. So change in entropy during a process from state 1 to state 2 for water as the pure substance or air as it undergoes the process from 1 to 2, the change in entropy may be found from these two relationships. 1 to 2 integral du over t plus 1 to 2 integral p dv over t, or 1 to 2 integral of dh over t minus 1 to 2 integral of vdp over t. Let us apply for liquids and solids. The Gibbs equation, the first Gibbs equation, which is TdS is equals to du plus pdv, or ds equals to du over t plus pdv over t. We'll try to apply this equation in solids and liquids. For solids and liquids, we know that the specific volume, it does not change. It is approximately zero. For solids and liquids, the change in specific volume is essentially zero. So this term would essentially be zero for solids and liquids, and change in entropy would be dependent upon du upon t. And if you remember the lecture on du for solids and liquids, you know du is essentially c dt. This is the expression for solids and liquids, because for solids and liquids, Cv and Cp, they are the same. So since Cp equals to Cv equals to C for solids and liquid, du equals to C dt is applicable for solids and liquid. So we can replace du with C dt in terms of solids and liquids. Furthermore, if we assume that C, specific heat, is constant for solid and liquid, we can have this as the constant outside, and we can integrate from 1 to 2. S2 minus S1, which is ds, is essentially 1 to 2 C dt. If we assume C to be constant or an average value for solid and liquid, we can have C average ln T2 over T1 as the change in entropy. This equation is applicable for solids and liquids. This is the first part. Entropy change expression for solids and liquids. The second thing is for an isentropic process. For an isentropic process where you have this expression for solids and liquids, isentropic process means ds is essentially equal to 0. So that means c dt over t is equals to 0, which means dt is essentially equal to 0. This essentially means that for solids and liquids, an isothermal process is essentially an isentropic process. This is what you should remember. Moving on to an example, let's say we have to determine the entropy change of liquid methane, again liquid, as it undergoes a process from 110 Kelvin 1 megapascal to 120 Kelvin 5 megapascal. Number one, using the tabulated properties, and number two, approximating liquid methane as incompressible substance. What is the error involved in the latter case? So the table is given alongside this example for liquid methane. This table is given for your ease. The expression is for P1 and T1, 1 megapascal, 110 Kelvin, the entropy value is 4.875. For second state, 5 megapascal, 120 Kelvin, 5 megapascal, 120 Kelvin, the entropy value is given to you 5.145. You can directly find out the change in entropy by subtracting S2 minus S1. This is directly using the table. Now, if you have to use the average values, so you will find out for this first condition, you will find out the Cp value. For the second condition, you will find out the Cp value. These two values are given to you. And you will use the expression. This is the average of the two values. And you will use the expression which says change in entropy is C average ln T2 over T1, which is the expression that we derived in the last slide. 120 Kelvin over 110 Kelvin. This is the change in entropy if you choose the approximated specific heat value. Now the error involved with regards to the tabulated value is essentially the difference of the two divided by the tabulated value multiplied by 100% would give you 12.2% as the error involved in using the average value or using the tabulated value. The second half now is for the ideal gases. This is the TDS relationship involving internal energy and PDV equation. If you remember, for ideal gas, change in internal energy is CVdT and ideal gas equation is P equals to RT over V. So du could be replaced by CVdT and pressure over temperature could be replaced by R over specific volume. Now, if you want to integrate, you would have to 1 to 2 CV dt plus R dV over V would give you ln V2 over V1. This is the integration for this expression. The other TDS relationship was ds is equals to dH over T minus VdP over T. Again, dH for an ideal gas is Cp dt and the V over T relationship, this expression could be replaced by R over P, which is this value dP. Integrating, you will have 1 to 2 Cp dt over T minus R ln P2 over P1. The important thing is how do you solve these portions to find out the change in entropy. There are again two methods to do that. One is the approximate analysis. Approximate approach means you take the average value of Cp and Cv independent of the temperature. We'll see how we can do that. The other is exact approach where you do the integration of Cp and Cv with regards to temperature and do the analysis. So we'll look at the two approaches one by one. The first thing is that you do the approximate analysis. That means you take Cv as a constant average value, Cv average value as a constant, and you take it out of the integration. So what you do is that you took Cv out of the integral as an average value, and you have the integration of dt over t, which is ln t2 over t1. Similarly, you took the Cp average value and you took t2 over t1 as the ln t2 over t1 as the integral of dt over t. Now, how do you get the average value of Cv and Cp? This is how you get. You will find out the value of Cp or Cv at the temperature T1. Sorry, you will take the temperature T1 and take the temperature T2. You will take the average of the two temperatures, and at the average, you will find out the value of Cp and Cv from the ideal gas tables. For example, table A17 for the air as the ideal gas. So CV average is essentially the CV value at the average temperature, which is the temperature average of T1 and T2. I hope it is clear. Is this point clear to you? We have already done this before. So far, is it clear to you?
Yes, sir.
Yes, sir.
All right. All right. Moving on, the exact analysis. How do you do the exact analysis? This is where you will have to integrate Cp dt over T, where you have a relationship of Cp and temperature available to you. But your life has been made easier in the sense that you don't have to do the integration yourself. There has been a table that has been developed for ideal gas with this symbol S naught. S naught value, which is integration of Cp dt with regards to temperature from 0 Kelvin to the Kelvin temperature given to you. It has been already calculated for you and tabulated under the C naught column. For example, if you look at table A17, for 300 Kelvin, S naught value is given to you. It has already been calculated and tabulated for you. That means for 0 to 300 CPDT is already been calculated for you and the value is 1.70203 kilojoules per kg per Kelvin. It has already been done for you. Now, let's say I have to do the integration Cp dt upon T from 300 to 320 Kelvin. One thing is I plug in the Cp in terms of temperature and do the integration myself. The other approach is that I split this expression into two halves. How? I split it into these two halves, 0 to 320 Cp dt upon T minus 0 to 300 Cp dt upon T. These expressions are the same. 300 to
Yes,
320 Cp dt over T can be expressed as 0 to 320 Cp dt over T minus 0 to 300 Cp dt over T. Clear enough?
yes, sir.
All right. So for this first expression 0 to 320, I can directly take the value from the table, which is 1.76690 minus 1.70203. So I don't have to do the integration myself. It has already been done for me. This means I can express my T1 to T2 CPDT expression in terms of this expression. I can split it into 0 to T2 and 0 to T1, and 0 to T2 is essentially S dot S naught 2 minus S naught 1. So I can replace this whole expression in terms of S2 minus S1 is essentially equal to S2 naught minus S1 minus R ln P2 over P1. Clear enough? Is this point clear to you?
Yes, sir.
All right. And the important thing you need to know, the entropy of an ideal gas depends both on temperature and pressure. And this S naught part, it represents only the temperature dependent part of entropy. So this is essentially dealing with the temperature dependent part. Pressure dependent part is this part. This you should know. Now let us have a look at an example which says that air is compressed from an initial state of 100 kilopascal 17 degrees centigrade to 600 kilopascal 57 degrees centigrade. Air, first thing, ideal gas. Initial state, final state. Determine the entropy change, that is delta S, of air during the compression process by using property values from the air table, and number two, the average specific heat. So this is exact analysis and this is approximate analysis. What you have to do is that the first is the exact analysis. So you will go directly to the table A17 S dot 2 S dot 1 S naught 2 S dot 1. So at 17 plus 273 Kelvin, what is the value of S naught 1? At 273 plus 57, what is the value of S naught 2? Directly take the values from the table, plug in the values. R is universal gas constant known to you, pressures are given to you. The expression would give you the change in entropy for air as an ideal gas. Clear enough? Now, the second part is where you have to do the approximate analysis. Approximate analysis is where you take Cp as the constant, but this is the average value. That means the average of T2 plus T1 divided by 2. This would give you the average temperature, and this average temperature, for this temperature you can go and read the Cp value from the tables that are there in table A2. Just plugging in the approximate values, temperatures are given to you, pressures are given to you. This would give you the approximate value, which is at least same up to the second decimal or the third decimal rather. Clear enough?